Hello everybody. Well, we've been talking for a wee while about generating electricity from wind power, wave power, from burning fossil fuels, and what they've all got in common is you need a spinning turbine to turn a generator, and the generator generates electricity. But how does a generator generate electricity? Well, in order to answer that question, we have to talk about these guys. This is a magnet. And on its own, it looks pretty dull, uninteresting. But there you go, that's a magnet. Now, I don't know what you know about magnets, but magnets will stick to things that are made of, well, that's a clamp stand. It's made of metal. But do magnets stick to all metals? I'm sure you've maybe got fridge magnets in the house. But here's something interesting. There's a 2p coin. My magnet doesn't stick to it. It's made of metal. But here's something else a bit strange. Here's a new 2p coin. Magnets will only stick to certain metals. And old 2p were made of pure copper. Magnets don't stick to copper. But new 2p are made out of a cheaper alloy of metals and then coated with a little bit of copper. So the reason a magnet sticks to a new 2p is because it's sticking to the cheap metal that it's made of. There's only 3 metals that a magnet will stick to. And those metals are iron, nickel and cobalt. So there's maybe some nickel in that new 2p. So magnets will stick to some metals. Now, not only that, but if I bring in another magnet, there's 2 magnets. Now, these magnets will either repel, or if I turn that one over, they will attract. Now, if you're not amazed by that, then I'm going to show you again. There's something a bit strange at work here. There is an invisible force at work here that's pushing that magnet. And there's an invisible force at work here that attracts those 2 magnets. Magnets are pretty strange. And magnets have got a big role to play in the generation of electricity. And a lot of these discoveries were made in the 1700s by accident, or just by guys messing about with this newfound phenomena called electricity. So I'm going to investigate that a little bit. Magnets, by the way, magnets are found in the ground. It's a form of iron that you can dig out of the ground and refine it and turn it into little magnets that have got all sorts of uses for things like your fridge magnets and door stops and all sorts of stuff. These are called permanent magnets. They stay magnetic all the time. Now, one of the earliest discoveries made when the pioneers of electricity were messing about with all things electrical was they discovered that you can make a magnet. And all you need is a little bit of wire. Now, that wire is not magnetic. I've wrapped it up into a little coil. Now, that wire is not attracted to a magnet. So it's not made of iron, nickel or cobalt. In fact, it could be made of copper. It's not attracted to a magnet. But here's the amazing thing. I'm going to take an iron nail and I'm going to wrap that piece of wire around the nail. Right, I've wrapped my coil around a nail and it is not magnetic. It is not magnetic. It isn't sticking. I've got a tub full of paper clips here and it's having no effect. But I'm going to connect the bare ends of these wires to a power supply. And we're going to pass an electric current through it and see what happens. I've connected my coil to this lab pack, which I've got set at 4 volts, and we're going to pass some electricity through the coil and then see what happens when we put it in that little tub of paper clips there. So I'll turn on the electricity, and then very quickly I'm going to pop it in there. And look at that. A coil of wire with electricity flowing through it becomes a magnet. And you call it an electromagnet. It's called an electromagnet because it needs electricity to work. And the advantage is, though, you can turn it on and off. Not only can you turn it on and off, you can make it stronger by increasing the voltage, which increases the current that's flowing through the coil, which makes it a stronger magnetic effect. So, very early on, when the pioneers of electricity and magnetism were doing their experiments, they found that when you pass a current through a coil, that coil becomes magnetic. Now, sometimes you'll see a magnet with 2 different coloured ends. And the ends of a magnet are called the North Pole and the South Pole. And the reason for the different coloured ends is so that you can see that if you bring 2 colours the same together, they will repel each other. So 2 North Poles will repel each other, or 2 South Poles will repel each other. Right? So that's them repelling. But opposite ends will attract. So we get that phrase in science, opposites attract. Either with electric fields or with magnetic fields, electric charges or magnetic poles. So opposites attract. So there's an invisible force field around that magnet, which we cannot see. But if I take a sheet of printer paper and put it over that magnet and sprinkle some iron, I've got some iron filings in here, a little powdered iron. If I sprinkle that over there, then you should be able to see that the iron filings show us a pattern. You should see a pattern of lines that's produced around either end of that magnet. And that pattern is showing you the invisible force field around that bar magnet there. So there is a force field there, it is invisible, and it can have an effect on other metals or other magnets. Well, a permanent magnet has got an invisible force field around it. And that invisible force field can attract or repel other magnets. And magnets can also attract materials made from certain ferrous metals. And examples of those ferrous metals are iron, nickel and cobalt. And there's a bar magnet with a magnetic field drawn around it. And the arrows on that diagram always point from north to south. Here's our little magnetic field pattern then when you sprinkle iron filings on top of a sheet of paper over the top of a bar magnet, then that's the pattern you would see. Now you could also make a magnet that you can turn on and off using electricity. That's called an electromagnet, and here's how you would make a simple electromagnet. You need an iron nail and a long piece of wire that you can wrap round that nail, and you want to connect the ends of that wire to a battery or a lamp pack. So there's an electromagnet there, connected with a switch and a battery. That's so that we can turn it on and off. And if you were to dip the end of that electromagnet into a tub of paper clips, it would be able to pick the paper clips up because they're made of iron. And the advantage is you can turn it on and off. If you want to make a stronger electromagnet, just use a bigger battery or wind more copper wire around it. Now, electromagnets have got all sorts of different uses there. There's four little pictures here. Top left there is a component called a solenoid. It's an electronic plunger. That's the sort of thing you use in electronic locks, like car central locking. Bottom left is a scrapyard electromagnet for picking up lots of scrap metal, moving it from one place to another. Top right, we've got an electric bell, where you use an electromagnet to move a little iron hammer switch it on and off very quickly, and that hammer will strike the bell on and off. And bottom right is an electric motor. So there's some of our uses of electromagnets. Electric bells, so like a school bell or your doorbell might have an electromagnet in it. A solenoid is used in any electronic locking mechanism. It's got an electronic plunger in it that moves in and out. So the likes of car locks, the school door locks are all solenoids, electronic locks. A relay is a remote switch that allows you to turn on a high-powered device, either using a very low-powered circuit or allows you to turn something on remotely. And our electric motor then, they're used in just about everything that rotates electrically, so fans, power tools, and of course electric cars these days. So there's our electric bell. How does it work? Well, you can pause and have a little look at the diagram if you like, but basically when you press a switch and a current flows through the coil becomes a magnet that attracts the hammer, the little striker, which hits the bell. Then when the striker moves, it breaks the circuit, which turns the magnet off, and the striker moves back. That then reconnects the circuit, and the whole thing repeats itself, and that will repeat for as long as you press the switch. Solenoid, as we said, is an electronic lock. When you pass a current through the coil, the magnetic plunger is pulled into the coil. That might unlock your door. And when the electricity is turned off, or if it flows in the opposite direction, the plunger moves in the opposite direction. So, an electronic lock, solenoid. There's our relay. This is where a very low-powered circuit can turn on a high-powered circuit. And these are used in things like stage lighting rigs or stadium floodlights, where you don't want to have to run huge, big, long, thick cables and loads of electricity. You can turn on a tiny wee circuit that just turns a coil into an electromagnet, and the electromagnet can close a switch which turns on a high-powered circuit. And there's our electric motor. So you pass a current through the coil, the current makes the coil into an electromagnet, and then that electromagnet interacts with the stationary magnets and it rotates. So that's some examples of magnetism and electromagnetism.